But actually, yes, thank you all for being here and for the invitation, Caleb. It's an honor and a privilege to be here at Syracuse. For those of those folks that couldn't make it, or the winter storm, too bad. Thanks to all of you for being here. Yeah, there's going to be no quaternion algebras, I think. But if you're interested in quaternion algebras, go to quadalg.org, the home for quaternion algebras on the internet, and you'll get more than what you bargained for. Instead, this morning I'd like to tell you about elliptic curves and ranks of elliptic curves. This is a little unusual talk in the sense that there won't be any theorems. Instead, I have to report on a controversy. Now it's weird to have controversies in mathematics, but it's also kind of exciting. We really don't know what the answer is. So we're at the stage of trying to decide what the answer should be. What I'd like to do first is to spend maybe the first half of the talk just motivating the problem, telling you what it is and why it's interesting. I'm guessing you guys come from all areas of mathematics, so you may not already care about elliptic curves, but after half an hour, I hope you really do, as much as I do. And then after that, I'll tell you what the problem is and how we are trying to address it. Caleb, is the mic okay?
Yep.
Awesome. You guys can hear me, right? Very good, very good. Okay, so this is joint work with Jennifer Park, Bjorn Poonen, and Melanie Matchett Wood. Okay, so let's talk about heuristics. Heuristics is a weird thing. Is there a heuristics environment in LaTeX? I guess they have theorem environments and conjectures, and heuristics, I believe, what I would like to try to convince you, play an important role in how we understand mathematical objects. So to get you to believe this, I have a quote by Michael Harris, who says, the goal of mathematics is to convert rigorous proofs to heuristics. The latter are in turn used to produce new rigorous proofs, a necessary input but not the only one, for new heuristics. Do you guys believe this? Do you use heuristics in your own mathematical work? This thing should behave kind of like this thing. What should we expect in this kind of scenario? If we didn't know anything else, what would we predict? You know, like that kind of shorthand. And it's often very helpful if you have a big or complicated mathematical object, or a series of them, and you want to try to understand them, like really put your finger on them. It's helpful to have a stand-in for them. Now this is done in science much more broadly, not in using the same kind of language, but the scientific laws are often just heuristics that have withstood the test of time. I mean, it's not like there's a proof of the law of gravity unless you assume something else and prove it from that. So you know what I mean? It's like why we measure two masses, they see with the inverse square law to determine their gravitational attraction, and then we declare that to be law. And so in a similar way, well, we won't declare any mathematical laws. We'll hopefully establish something we believe is true and then prove it. That's what mathematicians get to do. But in this kind of context, I hope that you will use heuristics to your advantage in your own research, and especially like when you give a talk or you're trying to explain an idea to somebody, you can say, well, this is how this should behave, or you can think about it this way. That's often a very powerful way to approach mathematical ideas. And so what we're going to do is try to model a really difficult problem, ranks of elliptic curves, by trying to develop a heuristic. So that's the goal for this morning. Are you on board?
Yep.
Great. Okay, so I guess first I just want to introduce my area of mathematics to tell you a little bit about why we should bother. I mean, otherwise it's going to be a long 55 minutes. So since the time of Datafantis, mathematicians have looked for solutions to algebraic equations in integers and rational numbers. So this really does go back to the time of the Greeks. We cared about questions like, can a square and a cube of a rational number or integer differ by 2? That's the kind of thing that people were interested in very early on. Is there an example of such a thing? I'll leave you to think about that. Are there right triangles with all 3 sides rational as well as rational area? So you want to have, and then what integers are the sum of 2 or 3 or more cubes? So that's another example where we're trying to study solutions to algebraic equations. Actually, although I'm setting this up as like an old historical kind of investigation, these kinds of things are still very much studied today. So even for this question, I don't know if you saw the press release, maybe I'm on too many number theory listservs, but 33 was written as the sum of 3 cubes, integer cubes. That was kind of an exciting result of my colleague Andy Booker. So this area is not one that's like Euclid's postulates or something, which is dead, but these questions, each one of them is interesting enough that we're very often still studying them today. So the list is, this is not just the only three, but there's many, many more. And I don't think it's unfair to say that we remain interested, probably on my end, it's more like an obsession, to understand structure of solutions to algebraic equations. Now I don't mean looking for solutions out of the real numbers or the complex numbers. I'm really saying integers or rational numbers. I don't think it's beautiful to say square roots of 2 in there, or at least I'll allow them for a while, hoping that I can somehow decide if something is true over the rational numbers. That's sort of my bias. But it is really beautiful to include, to really study equations. Another one that I probably should, you guys know other ones too, like Fermat's last theorem, little t, that led to Weil's proof of modularity of elliptic curves. So this is the area that we're working in. Okay, so how hard is this? Well, the first and enduringly interesting case is when you study solutions to a bivariate polynomial, so polynomial in 2 variables, and we can think of that as defining a curve in the plane. So if there's only one variable, how hard is it to find the rational solutions? I mean, if it's just a polynomial in one variable x, what do you have to do to find the rational solutions? You have to factor that polynomial one variable. Okay, so there's a rational root test, and okay, so that's not something I'm going to have a long lecture about. Somehow, as soon as you include another variable, it's, I was about to say impossibly hard. It becomes very difficult. Okay, the whole talk will be about that case. If you want to add more variables, then instead of a curve, you'll have a surface or a higher dimensional variety. That's also interesting, but way too hard. Way above my pay grade, for example. Come on in, you guys. Okay, so here are some of the expressions, the plane curves that we've seen in the previous slide. The first one is, can a square and a cube differ by 2? I guess you need the other one here. I didn't say which order they were different by. So you also want the -2 there. And can an integer be written as the sum of 2 cubes? That's the n equals x cubed plus y cubed. So that's what these equations look like. And we want to be able to plug in rational numbers x and y, or maybe we are even more rigid and we want integers x and y to plug in. That's what we're interested in doing, and we find it beautiful when we find solutions or we prove that there are no solutions. So that's what we're going to try to do. Now, in order to categorize these, I guess we have to decide where does it become easy and hard again, in that kind of like Goldilocks range. Where should we be working? Where's the frontier? So let's organize these by the total degree of the equation. So in this case, the degree of both of these equations is 3. That's no accident for reasons you'll see later on. We may want to refine by the degree of x and y in a little bit, but I just want the maximum of the degree of the monomials that appears in that equation. And we'll say, I guess as you would expect, as the degree gets higher, it should get harder. So let's see what happens with small degree. What happens if the degree is equal to 1? Can you guys solve this one for me? So if you have ax plus by plus c, how do you find all of the rational solutions? I guess there are some degenerate cases. If all of a, b, and c are equal to 0, there's not anything to do. If one or the other equations is 0, you get a vertical line or horizontal line. But anyway, you learn how to do this in middle school algebra, right? You, I guess, write y equals mx plus b and parameterize them that way. But you can visualize what it means to have a rational point there. Once you have one, you can find anyone on the line. All right, good work. We did one case already. What comes next? I guess that will be degree 2. It's going to take me a little longer to describe that scenario. Degree 2 is still, I guess it's an upgrade from middle school to something more familiar probably in your lives right now. If you're teaching these kinds of expressions, this is a full set of monomials you can have if the degree of your equation is 2. And some of you are teaching calculus now, or I imagine some of you will, or have recently. How much time do we spend talking about quadratic equations? Quite a lot, right? We describe it to our students as coming from conic sections, and depending on, I guess, the signs and what monomials actually appear, you might get a hyperbola, or a parabola, or a circle, or an ellipse, or sometimes a case that's degenerate, like a pair of lines. Okay, but that's how you should be visualizing the curve. So well, you could probably teach that as well as I could explain it. Now, in order to avoid the case of 2 lines, which, after all, we just dealt with, right? If there's two lines, you just parameterize them separately. At the origin, that curve doesn't have a well-defined tangent line, and it's sort of, in order to impose some regularity, you know, like by induction or to avoid degeneracies, we impose this condition that we require the curve C is smooth. And that just means that if you have a solution, so if your f of x, y is equal to 0, then you want, that would be a point, a rational point on the curve, you want not both of these to vanish, because that would mean that there isn't a well-defined tangent line. The approximation to the expression f at that point is 0, or at least you need a quadratic term in order to express it. And as you know from calculus, it behaves really differently whether you're smooth or not. So I need to impose that smoothness condition to avoid some degenerate cases that will arise. Sometimes they show up in nature like this, and you have to figure out how to address the singularities or the places where the curve crosses. But that's not the interesting thing for what we're going to study today. Okay, so let's, from now on, look at smooth curves. So we don't have something like a curve crossing itself or with cusps or something like that. Okay? So let's look at smooth curves of degree 2. What we're interested in is the set C of Q. So those are the pairs of rational numbers x and y, such that when you plug them into f, you get 0. And I've already said this, but now I'm making sure that it's defined on the slide. We are interested in the set of rational points on C. Okay? All right, well, what do you got to do? Sometimes the set is empty. Wouldn't be very interesting to study the empty set. You can prove a lot of things about the empty set that's not really worth proving. So how do you decide if an equation doesn't have any rational solutions? What are you going to do? I guess you could plug into the equation and see that it's never satisfied. And then maybe if you search for a really long time, you were led to believe that there are no solutions, but that's not really a proof. Okay, we're not yet at the need for heuristics, at least at this stage. What could be the reasons why there isn't a solution over the rational numbers? Let's think about that for a second. Okay? So maybe there's a visible reason why. So you could stare at an equation and say, oh yeah, there's no way there could be a rational solution. Okay? There is one, hopefully easy way to see. Does this equation have any solutions? Why not? This is a big auditorium, but an easy question. Just getting warming up. You guys awake yet? So if x and y are rational numbers, then they're real numbers. When you square a real number, it's always non-negative. If you substitute non-negative numbers, you can't get a negative number. Okay? In other words, there are no real solutions. Okay, so maybe we'll overload the notation a little bit and plug in other things other than q here. But if I plug in something else, I just need to put that here. Okay, so we could ask for complex solutions or integer solutions or things over q root 2 if we wanted to. Let's allow that in the notation. But in this case, there are no real solutions. The real solutions contain the rational solutions. So that provides one quick check. It's like complete the square in x and y, and then see if the signs are negative in the quadratic form that appears there. That's sort of how you check that. Okay? So we should only be asking if they're rational solutions if they're real ones. Okay, what else could go wrong? If you're a number theorist like me, the real numbers are a completion of the rational numbers with respect to an absolute value, and there are other absolute values that you can put on the rational numbers. Maybe that sounds too fancy. The other thing you learn in number theory is congruences can often obstruct solutions. So let me show you what that looks like. So I claim that there are no solutions to x squared plus y squared equals 2 except 1 plus 1 is equal to 2. Okay, I have a problem on this slide. Now the goal is to find out where it is. I think you'll see what the idea is, why there's a congruence restriction, but something's wrong in my proof. All right. Can we stop the tape? Okay, let me explain what happens here. You study the x and y, and you see, yeah, okay, I know where the issue is, and you'll see it too. All right, you study y, the set of solutions, modulo 2, modulo 4, modulo an integer n, either has a solution or doesn't have a solution. So in order to do that, maybe x and y have a denominator. So first let's clear the denominators and see what happens. So you write x is a over c and y is b over c. Just choose a common denominator. When you plug those in and clear the denominator, you get an expression like a squared plus b squared equals 2c squared. Okay, now a, b, and c are all integers. So So we can take that expression and reduce it modulo any other integer, n, and you can see maybe mod n, there are no solutions. Okay, so when I say mod n, of course there's only finitely many values for a, b, and c separately, so you can just plug them all in and see. All right, so in order to fix this expression, I need to replace the 2 by 3. Okay, so you have to mentally replace the 2 by 3, and we're going to change the proof here, but you'll see what happens. All right, so if you have a 3 there instead, let's imagine what could happen for the a and b not both. If a and b were both even, what would happen in this expression? If a was even and b was even, this whole left-hand side is divisible by 4. If this side is divisible by 4, well, okay, this one, if there's a 2 here, I know that c is divisible by 2, but I'm replacing this by a 3. Okay, so then definitely c is divisible by 2. Okay, but that meant that a, b, and c were all divisible by 2. Okay, but if a and c and b and c were all divisible by 2, as long as I did this by clearing denominators a minimal way, like a minimal common denominator, I will never have that situation. So I can assume without loss of generality that a and c are relatively prime, b and c are relatively prime, and all I need for this example is that not both a and b are even. Okay? So if we do that, what happens when you reduce modulo 4? So what are the possible values of a squared plus b squared? And we'll see how this one fails, but the other one succeeds. Okay, well I only have to plug in a is 0, 1, 2, or 3. If I plug those in, what happens when you square those numbers? The only things you get out are 0 and 1. Okay, so if they're not both even, that means and I'm summing them together, the only values are 0 plus 1 or 1 plus 1. Okay, so now you see I wrote congruent to 1 here. I forgot to include the case where they're both odd. Sorry about that. But if you replace the 2 with the 3, you get a contradiction in the expression of the equation. Okay? So that's an example where by clearing denominators and looking at integers, you see there isn't a solution mod 4, so there couldn't have been a rational solution in the first place. Okay, sorry about the typo, but it's sort of more instructive for me about how to be. You never find your own typos somehow? It's always like, okay. I hope that's clear. All right, so now comes the big amazing theorem. Well, maybe the first time you hear it's big and amazing. For me, it's like 20 years of my mathematical life is built around studying generalizations of this. But anyway, if there isn't a solution, it's for one of these 2 reasons. So either there's no real points, or there's some integer n where there's no solutions mod n in this clearing denominators way. Okay? And this is because of what's called the Hasse-Minkowski theorem, or sometimes called the local global principle. And what it tells you is that there's really a finite amount of effort that you have to put in to decide if an equation has a solution or not. And what that means is you have to decide on the integers n that you have to check to see if there is a solution or not. And those basically have to do with discriminants of equations, places where that divide the coefficients, stuff like that. Okay, so after that you can check by machine or by hand, and then you will be able to detect that there is a solution this way. All right, and even better than that, it'll tell you a bound in the box that you would have to search on the absolute value of x and y to actually find a solution. So that's the, okay, so despite the typo, I hope I conveyed what I hoped to on this slide, which is degree 2 isn't too bad. There can be no solutions, but if there isn't, there are ways for us to detect that as number theorists and you as general mathematicians. Okay, so what do you do if there is a solution? Maybe we want more. And I tell you, actually, we can do more. We can explicitly parameterize all solutions. So I'm not going to be able to tell you, here's one solution. I'm going to say, here are all of the solutions to the equation. So I have to describe what that means. We call that parameterizing the solutions. Here's a way of generating each and every solution. All right? So when I say parameterization, well, let's consider, for purposes of illustration, the circle. That's already a good... How do you find all the rational points on a circle? Have you guys done this before? You seen it before? Yes, no? Okay. Well, all right, you can see it again if you have, and if not, boy, am I glad to be the person to tell you. Okay. How do you write down how do you parameterize the circle? Okay. Now, I don't mean the real parameterization of the circle, which is what you may have been thinking or would tell your calculus students when you, like, integrate along a curve. I don't mean that. Cosine and sine are not going to help us to decide if there are rational solutions or not. Okay? I mean something else. I mean, here's a way of generating all the rational points, and I can't just say like, plug in values of theta for which cosine and sine are rational numbers. That is the problem. Okay? All right, so now I have a little link to show you, which describes this in a way. I'm really a believer in pictures to explain. So here is the picture of how you write down all solutions to rational points on the circle. Are you guys loving this video? It's not mine. All right, so what do you do? How do you find all rational points on the circle? Well, here's one. It's called -1, 0. As much as I seem to be struggling to do computation this morning, I can't check that 1 squared plus 0 squared is 1. Okay, great. So now that I have 1, that was sort of guaranteed by my checking if it was empty or not calculation that we did on the previous slide. Okay, now how do I find any other rational solution? I mean, maybe there's sort of like, I want to know that I get them all and I want to get them. Okay, so let's get them first. How do I do that? Well, all I do is I take my favorite line with rational slope through this point, and that line, like this line, is going to intersect the curve here at another point, and I claim that that point necessarily has rational coordinates. Right? You're seeing them in the examples here, but how would you check that? So I have some x squared plus y squared equals 1. I know when I plug in y equals, t times x plus 1, I get I'll get an equation in it starts in 2 variables, and then it becomes an equation just in x. And I have one root, which is x equals -1. That means the other root is necessarily a rational number. Okay, so does that make sense? So I take a line that intersects a circle, and I know one of the points is rational, the other point has to be rational. I mean, what else could go wrong? It's not suddenly going to introduce some pi's or something weird. But if I had a root 2 in there, I'd have to have a -√2, and there isn't enough room. Okay, but so you see, so that's how that works. But you could pick any slope that you like, t, draw the line, compute the point of intersection. Okay, but this goes both ways. If I ever had another point on the circle, I could draw the line between them, and that would have rational slope. So in other words, the way to imagine parameterizing all the points on the circle is just literally parameterizing. It's like this, in the sea of lines, you take those with rational slope, and then you get to see all the points. Okay? And that works totally generally. So it doesn't matter that it's the circle. If you took any degree 2 equation and you consider lines through a designated point. Now I need that point to start with, but of course I shouldn't be able to generate something from nothing. I have to check that it's empty. But once I know that it's not empty, then I can see all of the possible points, even if it was a hyperbola, parabola, or anything else. Somehow projectively they all look the same from our point of view. Okay, so that's how to, this leads to the Pythagorean triples in a nice way. And 3, 4, 5 is the usual example that's given. So 3/5 plus 4/5, 3/5 squared plus 4/5 squared is 1. That's the usual what you see in all of your mathematical lives. Maybe later on when you're fancy, you get 5 squared plus 12 squared equals 13 squared, and you divide the 13. This is all of the possibilities, including some of these exotic looking ones. But you can write them all down in a totally explicit way. Okay? So here's what this looks like when you write it all down. When you take the line through -1, 0 with slope t and compute the other point of intersection, this is what the coordinates are right here. Okay? And then of course, we also have to remember that we have this point to start with. I'm allowed to plug in every t, and every point arises for such a t, except for this point -1, 0. There's a little cognitive dissonance that I feel at this moment. Do you feel like I should be able to uniformly describe these things? I mean, I definitely think that, but I have my own reasons. It's a little annoying that you have to treat this point separately. Do you see a way to get it from this parameterization? It's sort of, what do I need to plug in for t to get -1 here and 0 here? If I plug in 0, okay, I get 1, so that's not it. I really, don't I need infinity? What if I take the limit as t goes to infinity? So then I'll get -1 here. And the limit as t goes to infinity of this expression is really 0, because it's quadratic on the bottom, right? My students would immediately L'Hopital's rule this, but we don't have to do that in good company. Okay, so what's happening there? Well, the slope of the line is the vertical line. So where does the vertical line at the circle intersect it? Well, it's like with multiplicity 2. So if you allow t to be infinity here, that would be a uniform description of this. And this is the kind of thing where, well, in geometry we say working affinely misses what's happening at infinity. We really should be working projectively. And I'm going to try to avoid saying that too much because the equations will speak for themselves. But I just wanted to convince you that there really was a uniform way of doing it. Is that a stretch or a question? No? This is a good time to pause for a question. Do you guys have any questions? This is a big auditorium, but I'm certainly happy to answer anything that's on your mind. We're about to increase the degree, so now is the time. Take stock of what we do. All right. Did I at least convince you degree 1 and degree 2 are well in hand? They're classical geometric ways of understanding what the rational solutions are, and I can tell you what all of them are, as long as I can detect that there's one in the first place. Okay, cool. Let's talk about higher degree then. I'm just going to go way big degree and talk typical. So here's the kind of shocker, but is really fundamental and like you get a fields medal for proving. The typical equation of degree greater or equal to 4 has finitely many solutions. This is a theorem of Volta's. To tell you what typical means, but okay, is that a surprise or is it sort of clear that as the expression gets more complicated, shouldn't it be harder to plug in rational numbers and have it equal to 0? I guess that's the intuition behind it. That would be the basic heuristic, okay? And it, well, it's a theorem of Volta's. I'll be more precise, but now I don't have to worry about parameterizing solutions. I just have equation, and I know that there are finitely many solutions, and the question is, how do I find them? Make the list of all of the points. Okay? So I'll try to be a little bit more precise right now. So if I look at the set of complex points on the curve, so I just take the set of solutions, x, y, and I look at the complex solutions. So that describes an open surface. By that I mean an open real surface, or maybe a complex one manifold. I'm trying to make a connection point with those of you who are working in geometry or topology. Okay? So locally nearby, because it's smooth, it looks like the complex numbers. So if you want to think about that as a real manifold, it's two-dimensional, or as a complex manifold, it would be one-dimensional. And I say it's open because we didn't take care of what's happening at infinity. So there will be something, t is going to infinity, or x and y are going to infinity, and we somehow need to keep track of that, or else we haven't, it's like we're missing something in our description. Let me just assert there's a unique way to complete this to make a nice Riemann surface. Okay, so this is called compactifying. You missed finitely many points, and you can plug them in a way such that the total space is smooth. Okay? So in this way, you get a compact surface. You can just think of it topologically as a real surface. And it's orientable because it came from the complex number. So at every point I know which way I keep my orientation. And then I have to ask you, what is the classification of topological surfaces? And the answer is, they're determined by the number of holes. And we call the genus of the curve C the number of holes that you get from this procedure. There's like 3 other equivalent ways of defining genus, purely in terms of differential forms and on. But anyway, this is for me a good link with how do I think about genus anyway. So here's the stock photo of a genus 3 algebraic curve over the complex numbers. It looks like something you put in your cereal. Don't you want to have like 100 of these with a little milk? Maybe some fresh fruit on top? Okay. So we're just counting the number of holes there. If the equation we started with, which was f of x, y, was already smooth at infinity in some sense, which is typical behavior, then the genus is just given by this expression in the degree. So if you start with something smooth and you make sure that when you tend to infinity, you do that in a nice way, this is what you get. So what are the genera for d is equal to 1 and d is equal to 2? That's pretty easy, right? The genus is equal to 0. And that means that topologically you have no holes, which means topologically you have a sphere. And that's why those 2 cases we were able to treat sort of at the same time. Okay? When the degree is 3, so those were the equations in the second slide, the genus is 1. When the degree is 4, the genus would be 4 minus 1, 4 minus 2 divided by 2 is 3. Okay, so that would be an example here. A degree 4 smooth guy would look like this honeycomb cereal or whatever. Sorry, I don't have any branding. Okay. And the theorem of faulting says that the genus is greater than or equal to 2, such as the case where the degree is greater or equal to 4, then the theorem of faulting applies if there's only finitely many solutions. Okay, so it's a totally different world than what we had before in genus 0, where either there was a solution or not, and if there was, we could write them all down. There's infinitely many. Instead, there's always finitely many, and the question is, can you find them? All right. So now I'm going to totally not talk about this. Okay, the talk is about elliptic curves, and I'm trying to set the stage to convince you that elliptic curves is where it's exciting. Of course, some amount of my time I'm also interested in this question, but if you wanted to tell if a higher degree equation has a rational point, and if so, to tell me the finitely many solutions, that's what we could ask. Y to the fourth minus x squared equals something, you know, whatever. It's a hard, open problem with many researchers actively working in the area. Okay, so what I'm trying to convince you is if you're interested in this kind of solution, boy, do we need your help. Okay, it's not an easy task. There's lots of arithmetic, geometry, topology, Galois representations, all usually like you throw everything in the kitchen sink. Somehow all of number theory is contained in trying to find a solution to this problem. We also don't even know if there's a Hilbert's tenth solution. So if you're interested in logic, we don't know if there's an algorithm that takes as input an equation with rational numbers and produces as output, yes, there is a solution, or no, there isn't. Even though we know by Hilbert's tenth problem that there isn't if I ask for an integer solution to an arbitrary number of variables. So it's sort of a very interesting, we lack things, but people are working hard. Okay, so that's the other extreme case. We did degree 1 and 2. Degree greater or equal to 4 is too hard. So what's left in the middle in our Goldilocks world, the porridge is just right, would be degree 3. So let's talk about degree 3. These will be our elliptic curves. So something very special happens in this case. The genus is equal to 1, right? From that, already d minus 1, d minus 2 over 2, that's equal to 1. Now, here's the kind of funny things. This set of solutions may either be empty, finite, or infinite. Okay, and it's so that's what we're going to be talking about. When should you expect one of or multiple of these behaviors? Sort of what in a family, or what could possibly happen? So first of all, I guess I have to start with the rational point. That's one part of the conversation. So I put an exclamation point to make sure that that's already hard. If I gave you an equation xy degree 3 and I said, is there a rational solution, that's hard. There are methods by computing the Jacobian and then looking at some, but that's not the place that I want to start with. I want to say, maybe I gave you an equation and it's clear that there's some small height solution, some small point that I can find to begin with. And the question now that I want to check is if there's finite or infinite. That's already itself a separately hard question. Okay, sorry about that, but let's start with a solution. If I have a solution, then there's sort of like a substitution of variables that's like a cubic form of completing the square. So there's some transformation of the variables that takes that general cubic equation and turns it into just one that's easier to study, simpler, and that you can wrap your head around. First of all, you can like eliminate a y cubed to make it just a y squared, then you can really complete the square. And what you end up with is an equation like this, y squared equals f of x. Isn't that nice? You really get to reduce the number of monomials by being careful about substitutions like this. And after all, if we want to find rational points and I have some rational maps between them, I can always study this guy and then move back to my cubic equation if I want to. Okay? So this is what the sort of a standard form is called a Weierstrass equation. And that doesn't look too bad, does it? Y squared equals f of x. The a and b are rational numbers. Okay. And then I asked at the very beginning that the curve C was smooth. Maybe not at the very beginning, on the third slide. What is the condition to be smooth here? Well, you need to take this expression, take its x derivative, take its y derivative, and say, could there ever be a solution where I'm a point and both of those things vanish? And this happens exactly when the discriminant of this polynomial is, it's smooth if this discriminant is non-zero. And so that's generically going to be the case. It's really hard on poor A and B to have the property that their discriminant is 0. So this happens most of the time, but you do have to check it. Otherwise, you're in a degenerate case. What would happen if f of x had multiple roots? Well, that means that there's something squared times a third factor. That something squared I can absorb into the y term. So I just have y squared equals a linear thing. and then I'm back into an easier, it's not degree 3 anymore. That's sort of the way that smoothness inductively allows you to work in the right setting. Okay, so there's the place where I define one of the main objects of my talk. This is an elliptic curve over Q. So at this point, I hope I convinced you that from the study of Diophantine equations, if we want to study rational points, it's a sweet spot. Degree 3 is something very special. And you'll also see why. There are other reasons why elliptic curves are special, but that's the main motivation for it. So here I just repeated the definition of the elliptic curve on the top. What happens when you take the set of complex solutions? If I've done my job, I explained to you that it was genus 1, which means it looks like a donut, not a honeycomb cereal. Sorry for all the breakfast food observations. This is these are like hollow honeycombs. So this is actually like a bicycle tire. If you're thinking, boy, that doesn't sound delicious anymore at all. Okay, so it's only a surface. It's not the thing that's filled in. It's really just a two-dimensional object. I tried to indicate that with the picture there. Okay, now why are these called elliptic curves? Where's the ellipse, you might ask? The answer is there is no ellipse. Well, there was a long time ago, in that if you studied the arc length on an ellipse, then you end up with something called an elliptic function. Don't ask your calculus students to compute the arc length on an ellipse, or at least not explicitly. You can do it on a circle, because then you end up with sine and cosine. But if you change the ellipse by not having like a semi-major axis to being too larger, then it's an integral you can't do in terms of elementary functions. So instead, they're called elliptic functions. There are two types, and they're called elliptic functions because they came from arc length elliptic, and those are connected to elliptic curves through the fact that they're doubly periodic functions, when you understand what those integrals are trying to tell you about the underlying Riemann surface. So that we owe that to Abel and Jacobi and the others, and Weierstrass, who were thinking about elliptic functions by just seeing what you could get by doing integrals, and because of that, they're called elliptic curves. Okay. For those of you who are analytically inclined, I do encourage you to think about elliptic curves as being the quotient of the complex plane by a lattice lambda. You're supposed, or as r mod z squared, you're supposed to see a circle going around this way, a circle going around this way, and topologically it's the product of those two things. So that is, it's about the simplest kind of object that you could work with. And it really has a lot of nice structure. I'm going to be interested in the arithmetic, but I hope I've already convinced you that somehow number theory needs all of these ingredients to understand the set of solutions. So in particular, we want to keep track of that. Okay, now my favorite part of elliptic curve is, given points, I can generate more points. And that maybe is the most exciting part of my talk, at least from one perspective. Do you guys remember that in the graphic of the circle, we took lines through -1, 0, and we were able to parameterize all the points? We could take any slope of a line that we wanted. In degree 3, instead of taking the lines through a point, what will happen there? I mean, it'll intersect in two other points, and I can't really be guaranteed anymore that they're going to be rational. So I can't take lines of any slope through one point, but instead if I take the line through 2 points, it will intersect in a third point, and again, if I have a cubic equation and 2 of the roots are rational, the third one is rational. So it's a different kind of expression for understanding the points. It's a group law. It says if I take 2 things, I can get a third thing. That sounds like I have an operation on my set of points, which is really exciting. Okay? So this allows us to generate points given a set of points, and I'm going to spend about 5 or 10 minutes showing you how beautiful and fun this really can be. Okay? So it's called the Chord-Tangent law on an elliptic curve. And here's my, favorite thing ever. So I don't know how long I can get away with just showing this. So here you see there are 2 points, you draw the line, and then there's this other part, which I'll have to explain and justify, which is you drop the point down. But any y squared equals f of x, if I have a solution, I can interchange the sign on y. So there's always some evident symmetry in the picture that way, and I'm taking advantage of it to improve the quality of my, my group law. So this was, I helped the Quanta folks. They did the animation, and I picked out the elliptic curve. We went back and forth a couple of times, so the credit goes to Quanta, but I feel like this was my contribution to studying the animation of elliptic curves. Are you sufficiently hypnotized, or should we spend another couple minutes staring at this photo? I never get tired of watching it. I guess I should. It's better than Lulu. Okay. So this is the group law. Yeah.
So which category does this one fall in? Are there finitely many?
Let's talk about it. Yeah. How many points do we need to generate all of them? Yeah, that's what we want to get to. I'll take that as a sign we should. Okay. So you can't take any slope of a line. I think I explained that. So here is the algebraic equations that describe the group law. It'll take me 5 minutes before we get there. I'll just think of one. How would you define the group law? So here's the official expression. I drew it on a blackboard because there was this Consanitas project, math and art. Famous people, not me, were asked, what's your favorite algebraic equation? And then they were drawn on slate, and then it was shipped around as a project of Dan Rockmore, and really beautiful equations. Mumford's expression for the canonical class on MG is beautiful. So there was the groupies project. Dan Rockmore's a colleague of mine. He's like, Kodamai Consanitas said, what's your favorite algebraic equation? I said, oh, obviously it's the group law on an elliptic curve. Okay? So I tried to compress it down onto one piece of a blackboard. So how do you find this expression? You're given 2 points, P and Q. I have to write down the slope of the line between those 2 points. So this is rise over run. Then I need to compute the third point of intersection. And what I do is I take this and I reflect it into the axis. And this tells me that R is equal to P plus Q. You'll see in the next slide why that extra step is necessary. There's always that kind of symmetry, and I'm taking advantage to make it really a group law. And here is the explicit expression. I encourage you to work it out, why this gives me the x and y coordinates of the third point given the slope of the equation. And all right, so there you go. You could plug this into a computer, and you only need very few additions and multiplications in order to succeed with the expression for the equation. So pretty cool. Oh my gosh, I don't know that I'm given the license to say things like this. One would be hard-pressed to find a more beautiful structure in abstract mathematics than the Chord-Tangent on elliptic curve. This is a sign I've lost my connection to reality. But anyway, that's the nature of obsession, I guess. Okay. Maybe for some of you who are interested in this kind of thing, I'm trying to connect with as many areas of mathematics as possible so you can see your favorite thing. If you do elliptic over a finite field instead of irrational numbers, this expression makes sense on the top here. I mean, I'm just like declaring lambda to be the difference of elements, so I just need a field. I have to be able to divide, but other than that. And in that situation, you would end up with a finite set of points with a group operation on it, and this is really useful in modern cryptography. So even there's a proposal for a quantum-resistant cryptographic system that uses supersingular elliptic curves, not the group law, but elliptic curves. So it's really exciting. So if you're interested in not just the abstract mathematics, but concrete application, and you want to make the internet more secure, whatever that means, cryptography, elliptic curve cryptography may be your answer. That's the number theorist's contribution to that conversation. Okay, so now officially I just want to show you this slide about P plus Q is equal to R. One way to think about the group law is when P, Q, and R all lie on a line, they sum to 0. So the reason why I need to subtract R from the other side, that's why I have to reflect on the axis. So the reflection in the x-axis corresponds to the negation operation in the group law. And I guess the question then, so there's some degenerate cases where you want to double a point. Here is the situation where the line only intersects the curve apparently in 2 points, but the answer is there's a third point that intersects that, which is the point at infinity. And that point at infinity, it needs to be put in both to for this to make sense in a uniform way, but also because we need an identity element in the group. So I warned you about projective equations. We were going to have to see what happens when we let x and y go to infinity. The answer is there's a unique way to compactify. There's really one limit when I let those points go to infinity. The limit is defined by the slope, and that slope happens to be vertical. So that's all that's happening at the point at infinity. But once I add that point, which is alternatively written O, or infinity, or 0, I apologize for the multiple notations, but they all have different ways of thinking about it. It's a little weird to say P plus infinity equals P. So sometimes people want to write P plus O, but O is also used in other ways. But it's at infinity. Okay, anyway, it's the identity element, so we could call it whatever we want to do. But after that, I want to include that in my set of solutions. And the conclusion is that it's really an abelian group now. So it's not just a binary operation that takes two things and outputs another thing. It's really a group law. So it's associative is the main content here, in addition to having an identity. So there's a theorem that says that this operation is associative. It doesn't matter if you add P and Q and then R, or you do P and then Q and R. Have you ever yourself checked an associative law? It's the kind of thing that nobody does in polite company. It's Bezout's theorem. There's one reason for it, but okay. Are you excited that it's associative? Okay, I didn't think so. The exciting thing is that it's a group. Okay, so to answer your question, it's not just a question of finite or infinite. Now I guess I have an abelian group, and that's more than I could say for just a set. That's really an upgrade. Okay, so what do you guys know about abelian groups? Let me just pause for one question. If there is one. This is okay. So this is one of the peaks in the talk where elliptic curves. I've tried to motivate to you and convince you that they're special among all algebraic curves by having group law. Now we want to answer the original question of the talk, which is, what are the solutions? Are there infinitely many? Are there finitely many? But I have a refinement, which is, what is this abelian group? Okay. Well, what do you guys know about abelian groups? You learned this in your algebra class, I'm sure, right? There's a fundamental theorem of finitely generated abelian groups, right? There are abelian groups that are infinitely generated and kind of scary. The complex numbers is an abelian group, not finitely generated. It's a set of points on an elliptic curve over Q, isomorphic as an abelian group to some uncountable. No. Okay, so the theorem of Bourdelle is that the abelian group E of Q is finitely generated. Okay, so now I do have to, now that I've stalled for you, what is the theorem of, the structure theorem for finitely generated abelian groups that everyone, the whole mathematical world is built upon somehow? There's like a, you guys remember? There's a torsion part and a free part. The torsion part is canonically given. You have to choose a basis for the free part. Okay, but let me make this really explicit. There's a finite subgroup, some finite abelian group. It's called the torsion subgroup, and some non-negative integer r, which is called the rank of the abelian group. In this case, the abelian group is E of Q, in such a way that this abelian group is the torsion part, so these would be like the elements of finite order, Z mod 2 plus Z mod 3 plus Z mod something like that, and then some number of copies of R. So those points have infinite order, and the R just tells me how many of those copies of Z there are in my finitely generated abelian group. So the torsion subgroup is a passion of many. It's fairly well understood, so not the topic of today. The rank is totally mysterious, this number R. Okay? So the question of whether or not there are finitely many or infinitely many solutions is what question about the rank? That's the question, is the rank 0 or not? Okay? And I'm claiming that it's mysterious, I'm going to have a heuristic. That's still where we're going. All right, so intuitively, the rank is the minimal number of points required to generate the group law, via the group law, the entire set of points. So in that hypnotic video, I started with 2 points, and that was all I needed to generate all of the points and sprinkled at the end. The rank of that elliptic curve was 2. If you want to be very precise, this is the maximum number of Z linearly independent elements in E of Q as a Z module. That's another way to make this totally precise, to avoid this issue of up to torsion. Okay? So now our question is, what should we expect for the rank of an elliptic curve? I guess sometimes it's 0, sometimes not. Yes, question?
What does rank 1 mean? Because you need 2 points to start, generally very close.
Yeah, that's a great question. There is a way of doubling. So if I have this point, instead of taking another point and taking the line through it, I take the tangent line at that point. So it's like Q plus Q. So I can double a point, and then I get a third point. Yeah. And I guess once I have a third point, then that's like 2 times P, and then I can add P plus 2P, and I'll get 3P, or I get, so then Z. So yeah, it's good question. It's really like the limit, as if I was taking 2 points together and adding them, and I imagine what happened with the line. Yeah. Okay. I just want to show you an example in case I was talking too much abstraction. Here is the quanta curve that I contributed. This is the equation for that curve that they didn't want to put on the quanta article because I guess you lose readers when you put equations. But I gain you because I've shown you the equation, right? Okay. So this is what a typical elliptic curve looks like. And here are a bunch of rational points. Now, atypically for this elliptic curve, as I just alluded to earlier, it has rank 2. And in this case, it has no torsion. So every point has infinite order. There's no point that I can double or triple or something and end back at infinity. Those are separately cool. But, so the statement here is that E of Q is generated by 2 z linearly independent points, which could be this point 0, 1, and the point -1, 2. Okay, and that was the hypnosis that I induced to you earlier with the lines that go across. And that was supposed to be a description of how you generate all of the points on this rank 2 elliptic curve. And actually, I picked rank 2 because I didn't want the reader to be hung up on doubling as opposed to just adding 2 points separately. But I hope that's okay. All right. I'm going to skip more information about this particular example because I want to get to my heuristic. Okay, so now, if I've kept you this far, what are the possible ranks of elliptic curves is now my precise question that I hope I motivated and I made it well defined. So that like when is the rank 0 or 1 or 2, we want to predict that. I don't have an answer. Sorry. But I will provide you a heuristic, which is better than an answer? No, all right. It's, maybe will help us to find an answer, is what I hope. Okay. So one question that you might ask is, are they unbounded? Can their ranks be arbitrarily large? That would already be the kind of thing you want to know about this set. Because if they're unbounded, maybe to be really precise, we should say for each rank, what's the probability that I get that rank? And ultimately I will get that. But already the question is, what are the possibilities for the rank? It seems like we should get that on the board, right? Okay, so I also don't know the answer to that question. But all right, let's see how far we can get. This question, in a different way, like divisor class groups on cubic curves, goes back all the way to Poincaré. I was charmed to see that because I didn't think of Poincaré as being an arithmetic geometer, but Poincaré was an amazing guy, so he also made this kind of contribution. That's as far back as we can find it. Mathematicians throughout the 20th century, Néron, Tate, Mestre, Silverman, Elkies, have argued both sides. I was just at a conference this week at the IAS, and I said, okay, what's the status? What do you guys think? Are they bounded or unbounded? And boy, the opinions fly. If there's alcohol involved, they're even a little more visceral, these opinions. Okay? But it's fun to be at those conversations. If you're ever at a table of mathematicians and they're enough number theorists, and you just want to get conversation going, what do you think about ranks? It's always a fun time. We don't know. There's a controversy. There's data that shows some number of elliptic curves of high rank showing up. So if you want to see how large can ranks get, what we know right now is there's an elliptic curve of rank 28 that was found by Elkies. It's assumed to be, it's 28 under GRH, with 28 or 30 unconditionally. So that's as large as we know that the rank can be, is 28. Okay? And I don't know if 28 feels like infinity to you or not, but I guess that's pretty big. So our contribution is that we propose a heuristic which predicts that the ranks are bounded. We'll also tell you what proportion of elliptic curves we think have a given rank. So in fact, our heuristic says that there are only finitely many elliptic curves over Q with rank greater than 21. So there could be infinitely many of rank 21, but this guy, which is rank 28, should be a member of a class of only finitely many. Okay, so I have to spend the next 15 minutes or so describing the ranks of elliptic, what our heuristic explains, but at least I made it as far as here. We're on team bounded, I guess. And maybe I want to try to convince you of that, but I hope you at least appreciate the context of the question. Okay, so I would like to make it precise right away by saying what do I mean about expectations and so on. What I'd like to do is to carve out a set of elliptic curves that's finite, ask that finite set what's your rank, and get a distribution, and then let that finite set go to infinity. So that will give me a probability distribution on the set of elliptic curves. To do that, I look at the height of the equation, which is just how big A and B are, in some sense. So here's our elliptic curve, y squared equals x cubed plus ax plus b. I could change variables if I have this weird situation. Well, first of all, I can clear denominators. And if I do that in a minimal way, so if a and b were rational numbers, I don't know, I multiply through by the denominator or power them and absorb it into the x and y terms. If I do that in a minimal way, like I would do writing a rational number in lowest terms, then I can assure that there's no prime p, that p to the fourth divides a and p to the sixth divides b. If I had that, I could pull a p squared out of this whole term and p cubed in this term. So in other words, there's like a minimal way to make these integers. And when I do that, the elliptic curve is uniquely determined by the integers a and b with this property. So in other words, to loop over all elliptic curves AB up to isomorphism, I just have to ensure this condition holds on the coefficients a and b. And once I have that, it's natural to measure the height. So I have some integers a and b, and I could just take the maximum of those. There's a certain weighting that is evident from the x and y. They are playing exactly the same role. So we define the height of E to be the maximum of 4a cubed and 27b squared. These are the two terms that appear in the discriminant. So I'm just taking the maximum of those two. So that's a natural measure of the size of the equation that includes the weighting. Okay. So is it clear that I have only finitely many elliptic curves of bounded height? Well, I bounded a cubed, so I bounded a. All right, same with b. Okay, this is just a natural way of keeping track of those. Here's a little notation. Let's keep track of the elliptic curves of height h with some script e. And I just convinced you, hopefully, that there's finitely many elliptic curves of bounded height, of that height at most h. And now we can ask a refined question. Given a random elliptic curve of height h, what can we expect for its rank? So to make that rigorous, you could do something like look at a slice of height h to 2h, or I could take all of them from 0 up to h, and then I could say what is the distribution of the ranks that I took out of them, or I could just, but I hope intuitively it's clear. Somehow we expect the rank to be a function of how complicated the curve is, and I'm claiming that if, as a coarse approximation or as a heuristic, a good measure of that complexity is the height. Okay, so, all right, so now this is probably the most technical slide in the talk. Did everyone get your brains to squeeze? Okay, I need to squeeze your brain in one slide. Is that, this always happens, 45, 50 minutes into the talk, that there's one super technical slide where the speaker black boxes something. It motivates our heuristic, so I apologize that if you find this terrifying, I try to black box it. If you want to know more about it and you're like, oh, why didn't he really tell me what the Selmer group was? Come talk to me later and be a number theorist, okay? But in case it gets stressful, you can take your brain and squeeze. So, the rank of an elliptic curve is hard to measure. Somehow the set of rational points is hard to get at. So what we do is we put it in an exact sequence with so it sits inside this abelian group with an error term with this Russian letter Shah. Okay? So this guy is isomorphic to z mod nz to the r. Right? If I take z to the r and I mod out by n, I get z mod nz to the r. So that's a way of like capturing the rank. I guess I also have my torsion subgroup. So just imagine n is co-prime. So I'm not going to be able to grab the whole guy, but I grab sort of up to n multiples. This cell NE is called the n-Selmer group of E, and its reason it's introduced is it is an effectively computable finite abelian group. So there's a machine that if you insert E and N will produce as output this finite abelian group, as opposed to the rank which I make no promises for. Why? Because there's an error term. That error term is the Tate-Shafarevich group of E. It's as like a class group of an elliptic curve, if you think number theoretically. It's a failure of a local global principle to hold. It's really they're ghosts, and the ghosts are measured by Shah. The things that look like they should come from points, but they turn out not to. Okay? If I knew that Shah was finite, then I could take n large enough and really discover the rank this way. It's not known if Shah is finite, but maybe we'll assume it while we're guessing heuristics. It'll be the least obnoxious thing that I assume along the way anyway. But what this means is there's already this abelian group actually sits naturally in the exact sequence. So if I was going to model things for you, it would be a little weird for me to model this without also modeling these things, which are really intrinsic to the study of elliptic curves. Okay? Now there are theorems and widely believed conjectures on the expected behavior of Selmer and Shah, which make predictions on this E mod NE. Okay, so I can't tell you all of those, but I'll tell you one of them. So here's the only thing you need to take away from this slide. As n goes to infinity in a precise sense that I won't tell you after 4 minutes of my talk, if you write down a random alternating matrix, so an alternating matrix of some size, so the size should be also going to infinity, with entries in Z mod NZ, so I just want it to be equal to the negative of its transpose, then SHA of E is modeled by the co-kernel of E, and this E mod NE is modeled by its kernel. Right? So this isn't, I mean, you sort of have to take n to be a prime power, and then this is a p-adic thing. Trying to hide that a little bit. That's what I mean in a precise sense. You guys know what, you know what kernels are. What's a co-kernel? It's the codomain mod the image. In rank nullity, if this were vector spaces, if n was a prime and these were all vector spaces, then if you took the image of this linear map A, then it may not be surjective. The co-kernel is how much you need to add to the image to get the whole codomain. So if a map is surjective, its co-kernel is 0, and otherwise, if there's something you didn't quite see, then that's measured by the co-kernel. Okay? So there's a massive amount of work that's gone into making predictions for this. You might think about it in some coarse ways like generators and relations, but they respect an alternating pairing. And the thing to take away here is somehow this group is measured by the kernel of a random skew-symmetric matrix with entries in Z mod NZ. And if you were to let n be a prime power, there really will be some heuristics and theorems in this thing.
Can I ask what size is of A? Is A
Yeah.
2 by 2 or?
A should slowly grow with n. Imagine that it's like log, which we know goes to infinity, but no one's ever observed it. So imagine it's like a 10 by 10 matrix that's slowly creeping up. And then there are theorems you can prove as the size of the matrix and the size of the entries go, with respect to a natural Haar measure, etc., etc. So it's not a fixed size, but it's slowly growing. Okay, so you guys can absorb this and remember a little bit. So if I wanted to get the rank here on the nose, boy, I wish I could get rid of this n. So here I have to take a matrix with entries in Z mod NZ, where there are kind of like theorems and conjectures about SHA and so on. So why don't I just replace Z mod NZ with Z? Then I would take the kernel of an alternating matrix with entries in Z, and if this is supposed to be true, or believed, or has some context in which it's not a totally crazy thing to do. So that's where our heuristic comes from. That's the moment where we make a leap from something where there are theorems over ZB and in a compatible way to something over Z. Right? Okay, and now you can relax your brain again. So here is an explicit description of our heuristic. It's supposed to be compatible with known structural properties of elliptic curves. So I need a function which measures the size, and I hope I'll be able to tell you something about it, but x and eta are supposed to be, x is going to be the size of the matrix entries, and eta is going to be the size of the matrix. Eta should be, so I want this expression to be about h to the 1/12, and what I mean by that is just it's bounded above and below by constants this way, and maybe I'll be a little more flexible too. This is a heuristic, but the 1/12, oh yeah, I want to say this. So the exponent grows very slowly in comparison to x. So that's what I mean. It could be a log thing. So the size of the entry should be growing, and the matrix should also be growing in some compatible way, but we're not going to be too precise except that it should have this relationship. The matrix size and the size of the entry should grow like some h to the 1/12 if I want to model the curve of height h. This calibration and where it comes from, I hope I'll have a chance to say something about it. But, so here is our basic model. If you take an elliptic curve E over Q with height h, you choose an integer n, which is approximately this eta, but I need to be careful about parity. So I take that integer, but I don't want to privilege even matrices or odd matrices in their dimensions. So I allow, basically, maybe eta is 10 and h is 10 to the 6th or something. So then I want to pick uniformly a random 10 or 11. Okay, so imagine n is eta, some moderate size, and I flip a coin and I either leave eta alone or I add one. Okay, and then I choose a random matrix with entries bounded of size x of h. So it's an n by n matrix. I want it to be alternating, and so have entries in this, integer entries in this interval. And I do that uniformly at random. I just write down the possible skew-symmetric matrices. So I guess I only have to choose the things above the diagonal. And then for those, I choose them randomly in a region, in this interval. So our heuristic says that as h goes to infinity, that the rank of the kernel of this matrix models the rank of the elliptic curve. So if I imagine a random E coming along of some height h, and I go through this procedure to make a random matrix and look at its kernel, then that should predict the rank. Where does this come from? It comes from the previous slide with the Z-mod NZs. There's also a thing for Shaw. Now, our model doesn't have any real justification. It's a heuristic. I guess I tried to tell you that on the first slide. But it's like an Occam's razor. It's sort of like a simple, random linear algebra object from which we can read off the arithmetic of the elliptic curve. Elliptic curves are nonlinear. They've got arithmetic, lots of stuff jammed into them, hard to understand. Let's replace that by a matrix of a given size, those measured by the complexity of the elliptic curve in its height, and then we can read off something like predictions for the rank of the elliptic curve. So that's, isn't this a weird way to do math, but kind of cool? It's sort of, we replace something with the model, and then let's see what the model says. So basic consequences of the model, I'll repeated the model at the top for you in case you wanted to remember. First of all, it predicts that the rank is 0, 1, or greater or equal to 2 with probabilities 50, 50, and 0. Half the time the rank is 0, half the time the rank is 1, and 0% of the time the rank is bigger than 1. What I mean by 0%, I mean like, well, it could grow as a function of the height, but it'll never grow as a constant multiple of the height. So it could be square root of h or something, but 0% of the time when you do this limit, you get rank 2. Why is that? If I take a random matrix with integer entries and I ask for the size of its kernel, what will you tell me? Typically, well, what's the determinant look like? If the kernel is going to exist, then the determinant has to be 0. What's the likelihood that if I take a random matrix, its determinant is 0? In any reasonable sense, the answer is 0% of the time. Now, these are skew-symmetric matrices, so you have to do something separate, but it's still true that if you take a matrix of even size, skew-symmetric, that 0% of the time it has a non-trivial kernel. But for skew-symmetric matrices of rank odd, something kind of weird happens. Like, what is a skew-symmetric matrix which is 1 by 1? A is transpose is equal to negative A. Oh, the only skew-symmetric matrix of rank 1 is the 0 matrix. All of those have a kernel. Okay, and in general, you can see that the dimension of the kernel has a skew-symmetric pairing, so it has to have even dimensions, so there's always something in the kernel. I think I said kernel, I meant co-kernel there. So any skew-symmetric matrix, the determinant is automatically 0, because A transpose is minus A, the minus 1 becomes to the n, so the determinant is automatically 0. Okay, that's the 50-50. When I flip my coin and I look at the dimension of the parity of the rank of the matrix, I get 50-50. So this is the precise sense that I would be measuring that. I look at elliptic curves up to a given height h, and this is what you would predict for the size of the curve. So this is the minimalist conjecture. It's widely believed, and you also recover predicted probabilities for Shaw. And to see more of the prediction of the ranks, there's ingredients here that I won't have time to get into, unfortunately. I think I'm going to zoom to the end just to make sure I have a conclusion slide. The point of the talk I just gave here was to show you about ranks of elliptic curves, to give you some idea that it's the number of z-linearly independent generators, and to convince you that nobody actually knows what the rank is supposed to be. We proposed a heuristic, which is a linear algebra heuristic, which captures the spirit of the arithmetic of the elliptic curve. And, well, it proposes that elliptic curves, the ranks of elliptic curves are bounded. I didn't quite have time to go through the details there, but I don't feel too bad about that. If you want to read about them, our paper is on archive, and I'll be here all day, and I'll tell you a little bit about what goes into computing the number of skew-symmetric matrices with a given rank. It's some concrete problem that requires a calibration, but the output is what I announced earlier, that the output of the model is ranks are bounded. In particular, we say that there are only finitely many with rank greater or equal to 22. And you know what? I still don't know what the answer is. All this says is if there's nothing we missed, ranks are bounded, but maybe we missed something. So there could be some family with special properties, And if you believe in your heart that ranks are unbounded, at least you can take that away from our conjecture that they really would have to be a very special thing. All right, thank you very much for your attention.
All right, we do have time for some questions if anyone has anything. I certainly have one at least.
Thanks, Caleb.
In which camp do you fit in? Or are you completely agnostic?
Well, I wrote a paper that says that they're bounded, so I wonder what my co-authors will think if I'm on tape saying that they are bounded. I'm going to just answer this in a different way. We have like a... Do you believe in the multiverse? Do you know what I mean about the multiverse? Maybe there are like lots and lots of universes where the number theory is a little different. Okay? In that world, in the multiverse, I am sure that ranks are bounded. And basically that's what our theorem says, is that if there's a random model that predicts this, with probability 1, the ranks are bounded. That's like a theorem that we can prove from the existence. So if truly elliptic curves look like this and there wasn't anything we missed. And so the only question is, which universe are we in that multiverse? And for that reason, it's hard to tell. When I was a graduate student, I was obsessed with ranks, and I spent a good year and a half trying to prove that they were unbounded by writing down geometric structures, understanding universe. So somehow in my heart, I want to believe that they're unbounded, but eventually you have to get a thesis and graduate and get a PhD, and so you can't just follow, sorry you guys, you keep the problems close to your heart, but get a thesis. Find a problem you actually can do something. As an advisor myself, I offer you that as if in order to get forward. So some way, I would secretly like to prove that they are unbounded, but I don't know that I will be able to, so got to get back to my day job.
Any other questions?
Yeah.
So for the elliptic curve of rank 28, is the height like a ridiculously big number?
Yeah, let's look at it. Oh, we're being blocked. Okay. So here are the rank bounds. You can't read that. Okay, now you can read. So here are rank bounds in history. And the rank 28 curve was found in 2006. You can see I clicked on it. There you go. Those are the points. I don't know, what do you think? When I see that, I don't see big numbers. Like, that's the kind of weird number theorist I am. Those are they're not too big. How close are we to infinity with that guy? Nowhere near infinity. It's really hard to tell. But as you can see, you can't just take a random number of that many digits and another one and hope to find these rational points. If there really are elliptic curves of unbounded rank, then they're going to have to, we won't be able to detect that by looking at the A and B. And maybe one way of saying it is if we had elliptic curves, and it's just the size of the numbers that matters to determine what happens with the rank. Our heuristic is trying to explain what would happen under a null hypothesis that way. But maybe there's something really special about this number on the x-coordinate. What do you think? 2006.
Maybe it changes. Maybe you put something 2018, 2019.
If you do the plot of rank by year, it's converging. So I mentioned that to Noam. I saw him this week, Noam Elkis, and I'm just like, boy, what do you got to get to work if you're going to make that. I mean, it's a step function so it's a big horizontal line for the past 13 years. But this doesn't contradict our heuristic, by the way. The real thing that would contradict our heuristic would be infinitely many elliptic curves of some rank. And there are also bounds for that kind of thing. If you want to know elliptic curves, not over Q, but over Q of T. I don't know if I can find it. They say infinitely many. Oh, this is torsion. Okay. Oh, all right. I won't be able to find that in this list. But there's all what's known is there are infinitely many elliptic curves of rank 19, which is pretty close to 21, but not quite there. So that's so far we don't have a contradiction on that one.
All right, for the sake of time, so we can find the room, let's thank the speaker again and